Now I'd like to introduce to you our featured presenter, Dan Boneh. Professor Boneh heads the Applied Cryptography Group and co-directs the Computer Security Lab here at Stanford. Professor Boneh's research focuses on applications of cryptography to computer security. His work includes crypto systems with novel properties, web security, security for mobile devices, and crypto analysis. He is the author of over 100 publications in the field and is a Packard and Alfred P. Sloan Fellow. He is a recipient of the 2014 ACM Prize and the 2013 Godel Prize. In 2011, Dan Boneh received the Ishii Award for Industry Education Innovation. Professor Boneh received his PhD from Princeton University and joined Stanford in 1997. Now I'd like to turn the floor over to Dan.
Great, thanks, Joe. So I'm excited to be here. Welcome, everyone. And I want to tell you a little bit about our work on cryptocurrencies and blockchain technologies and everything that we're doing in the space here. So I'm looking forward to this webinar. And if you have any questions, please type them in, and we will answer the questions in the Q&A session. So this is meant for you. If I say anything that's not clear, please feel free to ask, and we will answer the question right away. All right, so let's get started. So as Joe said, I'm Dan Boneh. I'm a professor here. I work on cryptography, computer security, and I've been doing a lot of work on blockchains over the last couple of years. It's a fantastic area, a lot of fun to work in this space. And I want to tell you a little bit about our work and particularly what excites me about this area. Before we get started, I wanted to mention that in computer science, we have a very active computer security lab, which covers lots of areas within computer security which intersect very strongly with blockchains. So let me just quickly explain kind of what we do. So I work on crypto, blockchains, things like that. We have Zakir, who works on measuring notions of security. Matej works on big data and security. We have folks doing static analysis, which is actually quite relevant to smart contracts, where you want to make sure that the contract actually does what it's supposed to do. And so we have a number of people working on verification of software in particular and smart contracts as well. David Mazieres works on operating systems and consensus protocols. In fact, the Stellar consensus protocol, Stellar is one of the largest cryptocurrencies out there. That consensus protocol was designed by David Mazieres. We have folks also working on IoT security. John Mitchell works on various aspects of protocol design and programming languages. Programming languages are also a big component of blockchains. Again, the question is, in what language do we write smart contracts that are then executed on the blockchain? And that's a fantastic area that's growing quite rapidly. And then Mendel works on VMs. So there's a very active security lab. But in this webinar, I'm going to focus specifically on our work on blockchains and what we've been doing in the space. So what I'd like to tell you a little bit about today is basically a couple of things we've done. One thing I'll tell you about is something called confidential transactions using a system called Bulletproofs that we developed. And we'll talk about all the applications of that and where that came from. And then I want to tell you a bit about what are called proofs of solvency, which is how to prove that a cryptocurrency exchange is actually solvent and can cover all of its obligations. Then we're going to switch gears and talk about an application that's actually not directly motivated by blockchains, but is relevant as well. I'll tell you about a system called Prio, which is used for privately aggregating statistics. Everything I say here is work that's available in papers that are published in public. You guys, I'll have links that if you want to read more about the work, you're very welcome to. And as I said, if you want to use any of this, this is all public domain, and we'd be happy to answer any questions you have about deploying any of these techniques. Okay, good. So let's start with bulletproofs and confidential transactions. This is joint work with my student, Benedict Bunz, as well as our collaborators, Jonathan Boodle, Andrew Palestra, Peter Woolley, and Greg Maxwell. Andrew, Peter, and Greg are in a company called Blockstream, and they're actually also some of the core Bitcoin developers. Okay, so this is work that appeared earlier this year. I have a link here to the paper in case you want to learn more about how bulletproofs work, but let's get right to it. So I guess before I tell you about bulletproofs, I want to talk a little bit more broadly about blockchains and cryptocurrencies in general. It's an area that, from my point of view, is a fantastic area to be working in. The this area, though, kind of suffers, as you may know, a little bit from overhype. But nevertheless, there are real scientific problems here. And just to give you, and that's kind of what attracts me to the area, kind of the hard scientific questions that need to be answered. I can tell you that literally every project that I talk to in the blockchain space, I walk away with 3 new research problems to work on. So there are really lots and lots and lots of open questions, which is kind of great for a researcher like me. So just to tell you kind of the things that attract us to this area. So there's need for new consensus protocols, when we'll talk about consensus protocols in just a bit. And this is generally kind of work in distributed systems. So developing new consensus protocols. I already mentioned there's a lot of demand for new programming languages for programming smart contracts. And along with programming languages for smart contracts, there's also need for verification tools. So how do we verify that the contract does what it's supposed to do, so we don't end up with a situation like the DAO, where because of a programming bug, a lot of money was stolen, or like other famous contracts where because of a bug, a lot of money was locked up, so no one could actually access those funds. So verification is becoming quite a central area of smart contracts, and as I said, there's a fair amount of work on that here. There's obviously a need for new cryptography. That's kind of my bread and butter. That's where I live, and that's where I'm going to talk to you about. And then there's also really beautiful work in what's called mechanism design, or more generally, this area called algorithmic game theory, which is essentially how to distribute rewards and how to design incentive-compatible mechanisms that encourage players to act honestly and contribute well to the system. So all of these are wonderful areas where the blockchain introduces new research problems. So there's really a lot of new science that's being created here. In my opinion, of course, this area is, like I said, a wonderful area to work in. It's not a fad. It's an area that's here to stay, and it's going to be with us for a long time. As I said, in this talk, I'm going to focus on some of my work, which is basically kind of new cryptography that's needed for cryptocurrencies. Yeah, so I hope this will all be clear and exciting to you. And like I said, I'd be happy to answer any questions that you have at the end of the talk. Okay, so let's get to it. Although I do want to say that because of all this kind of scientific interest, it turns out there were many people working on blockchains around the university at Stanford here. And so what we did is we created this new Center for Blockchain Research. It's called CBR, the Center for Blockchain Research. If you want to learn more about the CBR, please go to cbr.stanford.edu. There's a lot of information there about what we do. In particular, this is a research-focused effort, but in addition to our research, we run a lot of outreach activities, including courses and MOOCs and books and seminars. So there are a lot of activities. All our activities are open to the public, and we want people to come and kind of join our activities here on campus. So please go to cbr.stanford.edu to learn about our outreach activities. Particularly if you go to the seminar page. There are instructions there on how to add yourself to the mailing list just to learn about activities that the center runs. I promise it's a very low volume mailing list. All you will get is just emails about events that are open to the public that you are all welcome to come and participate in. In particular, in January, we're running our 3rd Stanford Blockchain Conference. If you want to submit a paper to that, if you want to present some of your work, there are instructions on how to submit papers. If you just want to come and learn, you're very welcome to. As I said, this is in January, open to the public, and anyone can come and participate in the conference. If you come to one of these events, you kind of realize there's so much energy in the blockchain space. Even though it's a technical conference, it's really fascinating to hear all the conversations, the talks and the conversations in the hallway. And again, I can tell you that a lot of our brightest students now are going into the space, and with so much talent in the blockchain area, it's almost guaranteed that good things are going to come out of it. So I do want to mention that our Center for Blockchain Research is sponsored by sort of the top projects in the space: the Ethereum Foundation, Protocol Labs, Interchain Foundation, Amisago, Definity, and Polychain Capital. So it's been great to work with them. And as I said, we're always looking for more folks to work with. If you have any questions about a project that you're interested in, please reach out, and we would love to talk. Okay, so with that, let's get started with the technical part of the presentation. And I guess I'll start by taking on a challenge that someone asked me recently, which is to define a blockchain in 10 words or less. So what is a blockchain? Yes. So let me try to define it in 10 words or less, and then we'll kind of dig into the words. So a blockchain really is a data structure that has a number of critical properties, right? So the properties are basically liveness, which means that anyone can write to the blockchain and there's no way to prevent you from writing to the blockchain, right? We call that liveness. When you write to the blockchain, obviously sometimes there's a transaction fee associated with that, but if you're willing to pay the transaction fee, you cannot be prevented from writing to the blockchain. So that's liveness. Persistence means that once the data is written to the blockchain, it can never be removed. And typically, the way we achieve persistence is by replicating the blockchain, this data structure, replicating it many, many times all over the world, so that if you're going to remove something from the blockchain, you have to remove it from all the replicas or a majority of the replicas. So that's persistence. And you notice there's a little star there, because typically persistence is achieved under certain assumptions. Basically, say the adversary has less than 51% of the computing power in the network, or there are other ideas that are coming up about less than a certain amount of the stake of the funds in the network, less than a certain amount of the space that the network uses, and so on and so forth. But persistence typically is achieved under certain assumptions. And once you have liveness and persistence, the other important property that's implied by that is what's called consensus, which essentially means that anyone that's using the blockchain agrees on the current state of the blockchain. That is, we all agree on what data currently resides on the blockchain. Okay, good. So those are kind of the three properties that that blockchains provide to us. But fundamentally, I want you to remember, it is just a data structure for managing data, and it just happens to provide these properties. Now, these properties enable a tremendous number of applications. The simplest one in some sense is a cryptocurrency, right? If you have liveness and persistence, essentially this means that if somebody sends you money, there's no, a crypto token, say, there's no way to undo that transaction because of the persistence properties. Or rather, I should be more precise, there's no way to remove the transaction from the blockchain because of the persistence property. Of course, you can, if you wanted to, you can send the money back and undo the transaction, but there'll be a log of the fact that money was sent to you and then money was sent back. So persistence is kind of necessary for a cryptocurrency application. The liveness property means that no one can prevent you from spending your funds once you actually decide that you want to spend them. Okay, so that's why a currency is a very natural application for a blockchain data structure, but it also enables a whole bunch of other applications like what's enabled by smart contracts. It enables crypto asset management. So once I own a particular physical entity, I can record that on the blockchain, and that can never be taken away until I actually transfer ownership to somebody else. You can also talk about crypto asset management for digital goods, and I have to mention there's a game called CryptoKitties, which is where people trade digital kitties for fun, and it's actually a pretty amazing game. I encourage you to check it out. It's a really, really well designed game where people can buy kitties and then trade them later on, breed them with other kitties and trade them and so on. That's a wonderful example of a digital asset that managed on the blockchain. Essentially, who owns which kitty is recorded in this data structure, and once you own a kitty, no one can take it away from you, even if the company that runs the CryptoKitties game goes out of business. Yeah, so you will always own this kitty, and no one can take it away from you, and that's kind of the power of the blockchain. Okay, good. So crypto asset management is another application. I have to say that there's a lot of interest in the Stanford registrar's office in putting Stanford transcripts on the blockchain, and there are a lot of benefits to that. So, for example, you can always, if you present your transcript to an employer, the employer can always tell that it's looking at the latest version of the transcript, because the latest version is recorded on the blockchain. So there are a lot of benefits to putting contracts on the blockchain just for the purpose of freshness. So you know you're looking at the latest version of the document. And again, even if the unthinkable happens and for some reason the Stanford is no longer around, your transcript would still be on the blockchain, and you can still prove that you are a Stanford graduate. So again, the persistence is what is such a powerful mechanism that makes the data structure so useful. And of course, everything is transparent. The blockchain, all the data on the blockchain is public. The whole world can see it. So there are a lot of applications that require transparency, and blockchains are a wonderful data structure for those. Just to give you one example, if you want to run a lottery, for example, if you want the lottery to be transparent, so that you are guaranteed that the randomness that went into the lottery really is unbiased randomness, then again, a transparent data structure like a blockchain is a very good data structure to use. Yeah, so I kind of walked through a number of applications. There are many others, but this is why there's so much excitement about the space, in that there's this. Like I said, there's this data structure that's now available out there. It enables us to do things we couldn't do before. And again, that's why so many people are building new applications, and why so much talent is going into the space. All right. So with that, let's kind of drill down a little bit. And I guess what I wanted to do, even though there are lots and lots of blockchains out there with very different characteristics and very different designs, I wanted to just pick on one and drill down a little bit more, just to show you how it works. So, the one that I just chose is the Bitcoin blockchain. Maybe that's the most well-known. But again, I want you to remember, Bitcoin is just one example of a blockchain. In fact, we consider this a generation 1 blockchain, in that it's very limited in its capabilities. Generation 2 blockchains are things that are things like Ethereum, that include smart contracts and other capabilities. And Generation 3 blockchains are the ones that are being developed and deployed now. Those are ones that kind of avoid the expensive proof of work that's needed to make blockchains work. And we'll talk about that a little bit later. Okay, so let's talk about the Bitcoin blockchain, just so that we start at the beginning. All right, so the Bitcoin blockchain basically is, as the name implies, it's basically a sequence of blocks. Yeah, so you can add blocks to the blockchain at will. In fact, every 10 minutes, a new block is created. And these blocks basically form this very, very long chain. Yeah, it's basically from the beginning of time, since 2009, these blocks have been added every 10 minutes. So there are many of these blocks. And the reason they form a chain is because you notice when I look at block number n-1, that the block header contains in it a bunch of transactions. You can see there's a whole transaction tree that's embedded in the block header. This is what's called, this tree here is what's called a Merkle tree, which means that essentially all of these transactions that represent the block, and we'll talk about transactions in just a minute, essentially they are sort of committed to in the block header. Yeah, so this value here is a hash value that commits to all the transactions that are embedded in this particular block. There's what's called a nonce, which is related to the proof of work. I won't talk about that here. There's a timestamp, but the important field in the block header is what's called a hash. So what is this hash? Basically, every block is in every block, what you do is you hash the block header. Yeah, so you compute some sort of a compressed function of the block header, and then you write the resulting hash value into the hash field of the next block. And this is what forms the chain structure. Yeah, so you can see here, again, block number n contains a hash of block number n-1. Block number n+1 will contain a hash of block number n. And so we get this very, very long chain structure where this hash operation induces sequence among blocks, and that's why we call it a chain. As I said, this is only generation 1 of the blockchain structure. There are many new ideas being considered now. In particular, rather than using a chain, people are talking about using more complicated graphs. But here, let's just keep it simple and just talk about the Bitcoin blockchain. Okay, so that's what the blocks are. Now, you notice there are all these transactions here. So every block has a number of transactions. Typically, there are between several hundreds to several thousand transactions in a particular block. So let's talk about what these transactions are. And a transaction, again, just to give you a sense of how they work, I'm not going to talk about the specifics of the transaction format, just to give you a sense of what they are. Essentially, every transaction corresponds to a transfer of, potentially a transfer of funds between addresses in the Bitcoin network. Yeah, so what happens is in a transaction, we have these inputs to the transaction. These are kind of the addresses that provide funds into the transaction. So in this case, there are two transaction inputs. And then the transaction has transaction outputs, which are basically where the funds are going. So every transaction output basically has a value, which is how much money is being transferred to this particular address, and then it has the address, which is where the funds are actually going. All right, so transaction outputs contain value and address. And in this case, there are two transaction outputs. We call these things UTXOs. UTXO stands for unspent transaction outputs. So here we have UTXO number 1 and UTXO number 2. Okay, So what happened here is this transaction basically created two new UTXOs. These UTXOs belong to, address number 1 and address number 2, and each one has a certain value associated with it. Now, later on, if you want to spend money from a particular address, you actually don't spend money from an address, you actually spend money from a UTXO. Okay, so there are no accounts in Bitcoin, no accounts. Funds are actually held by these UTXOs. And what this means is that when you want to spend money from a UTXO, essentially you create a new transaction. Here we have one transaction input going in. This transaction input essentially points to the UTXO that's being spent. Okay, so the value that's going into this transaction is the value associated with the UTXO. And then there's a signature by the owner of the address that says, yes, I'm authorizing the spending of this UTXO. All right, so remember, you have a secret key that essentially allows you to spend the UTXO, and only you can cause a UTXO to be spent, or rather only whoever owns the secret key that's able to create the signature is capable of spending a particular UTXO. So it's kind of cool in that no one can take your funds away from you other than by taking your secret key. So if you keep your secret key safe, no one can ever spend your funds. And by the way, I should say that there's a whole industry forming around custodial services for holding secret keys for cryptocurrencies. So if you happen to own a bunch of cryptocurrencies, maybe it's an investment, maybe because you're an enthusiast, or maybe because you want to use the cryptocurrencies for something, the question is always, where do you store the corresponding secret keys that enable you to spend those funds? You can store them at your home if you want. But if something happens, and I don't know, maybe there's a burglary, maybe your home, maybe something happens to your house, maybe you lose the secret keys in some way, those funds can then be spent on your behalf. And so there's a whole industry of custodial services where you can give them the secret key and they will manage and store it for you. So keep in mind, it's probably a good idea not to store cryptocurrency secret keys yourself. It is probably a good idea to give it to a custodial service, and this is their business to keep those secret keys safe and make sure that they're never lost. Okay, so regardless, so we have these transaction inputs that basically authorize the spending of a UTXO, and here we have the two new UTXOs that are being created. So for example, here you see UTXO number 3 was created, and the interesting thing about the UTXO model is it's not account based. So funds are held in these UTXOs, which means that after you spend the UTXO, that UTXO dies. Okay, so no one can spend funds from that UTXO anymore, and it's as if it never existed. Okay, so this would be called a spent transaction output as opposed to an unspent transaction output, and no one can ever spend funds from that UTXO again. Okay, so that's how funds are basically held on the blockchain, and that's how they're being transferred from address to address. They're held in UTXOs, and a transfer means creating another UTXO. Okay, so that's the UTXO model. So that's how the Bitcoin network works. It's a pretty interesting model, although I have to say other blockchains actually use an account model where funds are actually held in accounts. And if you wanted to see how much money you have, you basically check how much money is in your account. In Bitcoin, if you wanted to see how much money you have to sum up all the UTXOs that belong to your address, and that will tell you how much money you have. So it's a little harder to tell what your balance is, but at the same time, this model is actually quite clever, and that it makes it quite easy to manage what's live on the blockchain and what's not live on the blockchain. Okay, so that's the UTXO model. Let's dig in a little bit and look at a particular transaction. So here I just listed one random transaction from the Bitcoin network. And the thing that I want to point out here, which is quite interesting, is again, you can see the addresses here. You can see the exact addresses that provide the funds. Okay, so this is one address that provided the funds. Here's another address that provides the funds. And here's how much money was being transferred in. So in this case, it's 0.5 Bitcoins, and then the other address provided 1.47 Bitcoins. Okay, so you can see exactly how much money came in, and then you can see where it went, right? So it went to this address, 0.01 went to this address, and then 2 Bitcoins went to this address. So you can see exactly which addresses contributed funds and which addresses received those funds. And I can tell you that there's a lot of work out there that shows that in fact it's not difficult to map addresses to physical entities. So there's no anonymity in these addresses. It's actually not that hard to figure out who these addresses belong to. So literally you can tell who transferred funds to who and how much. So the amounts are all public. So And remember, these transactions all go on the Bitcoin blockchain, which is then replicated all over the world and is public for anyone to see. And it's important that everyone can see the blockchain so they can verify that all the transactions are legitimate. And we'll talk about what legitimacy means in just a minute. Okay, good. So the problem with this is that the fact that all these amounts are public is somewhat contradictory to business needs, right? So for example, if because everybody can see who the payer is, who the payees, and what the amounts were, this is problematic for business needs, right? So for example, if if Stanford wanted to pay my salary in cryptocurrencies, effectively, in a Bitcoin cryptocurrency, say, effectively everyone could see what my salary is. Yeah, so the salary would be public. So that's kind of contrary to what a lot of businesses need. Even worse, like for example, if you wanted to manufacturer wanted to pay its supplier in cryptocurrencies, or in Bitcoin in particular, everyone will be able to see how much the manufacturer pays for the goods. So Ford, for example, would have to reveal how much it pays for tires, just as an example. So again, this is kind of counter to how to business needs. Generally, this information needs to be kept secret. And so the question is what to do. So can we adapt these existing cryptocurrencies so that maybe it's okay to reveal who the payer and the payee is, but it's not okay to reveal what the value is, right? So it's okay to say that Stanford pays me my salary. Everybody knows that I'm a Stanford professor. What's not okay is to reveal what my salary is, just as one example. Yeah, so that's our goal. So can we kind of hide what the amounts are in the transactions? And this is what's called confidential transactions. So confidential transactions is basically the idea of, instead of having the amounts be available in the clear, like you see here, the amounts are actually in the clear, the idea is to actually hide what the amounts and yet make it possible for everyone to verify the transaction. Okay, so what are we going to do? Well, instead of writing the actual amounts in the clear, like we do here, we're going to write something else onto the blockchain. Instead, we're going to write what's called a commitment. So what is a commitment? So here, I have to do a little bit of math here. I cannot give a talk without doing some math. So let me explain what this means. So if you look at the amounts here, you see it says 0.533 Bitcoins. Instead of writing the number 0.533 in the clear, instead what we're going to write is the number 533 in the exponent of some base. Yes, we're going to write g to the power of 533 multiplied by some sort of a random value that hides what the value is. Okay, so this is what's called the commitment. Yeah, so I'm committing to the number 533, which was the amount that's being transferred. But anyone who's looking at the blockchain has no idea what the number is that I committed to 533, because this number has been blinded by this random number here, by this h to the r1, where r1 is a totally random number. And I do the same thing. You can see this is a transfer of 1.478. Well, I'm going to write g to the power of 1478, right? So I'm committing to the number 1478, but nobody can tell that that's the number that I committed to. And the same thing on the outputs. And one thing that's interesting is actually that the fees are still going to be, you notice that, let me kind of jump here, the fees are still available in the clear, so everybody can know what the miners were receiving, but everything else is hidden. Okay, so let me just say a few more words about this commitment. This commitment is what's called a Pedersen commitment. It's a very basic mechanism used in cryptography, and when you want to commit to a particular value v, again, like I said, you put v in the exponent and then you blind it with some random number h to the r. Okay, so by looking at the number, by looking at the commitment, you learn nothing about v, but whoever committed cannot change the value of the number v. That's the idea. Okay, so now we get this more privacy-preserving blockchain in that no one can tell what amounts were actually transferred. So again, Stanford can pay my salary. No one can tell what my salary is. But now we run into an immediate problem, which is, well, since the amounts are hidden, how do you validate the transactions? In particular, what does it mean to validate a transaction? What you have to check is that the sum of the inputs going into the transaction, right, the sum of the funds going into the transaction should be equal to the sum of the funds going out of the transaction plus the transaction fee. Right? That's kind of a fundamental equality that has to be held, has to be true for every single transaction. When the amounts were available in the clear, everyone could just look on the blockchain and verify that all the transactions are valid. If the transaction was not valid, the whole block would get rejected. and thrown out of the blockchain. But now that the amounts are commitments, they're not actually available in the clear, you can no longer verify that this property holds. So we have kind of a fundamental problem, and the question is, what do we do? Okay, so this is kind of where the beauty of cryptography comes in. And so what we're going to do is we're going to use a little bit of crypto magic, and the crypto magic we're going to use is what's called a zero knowledge proof. Okay, zero knowledge proof. So what is a zero knowledge proof? A zero knowledge proof is something that allows me to prove to you that a certain fact is true without revealing anything else about that fact. So you learn, you have confidence that the fact is actually true, but you have no idea about anything else. Yeah, that's kind of the magic of zero knowledge proofs. And let me explain what we do here. So again, even though the public doesn't know what the amounts are, whoever creates the transaction can convince the public that this equality actually holds without actually revealing what the input and output values are. So that's one thing. So you have to convince the public that this equality star actually holds. It turns out there's another property you have to prove, which is that in fact, it's not just about the equality. The other property you have to prove is that all the values are actually positive. Yeah, so it's not just that the sums are equal. You want to make sure that none of the output values are negative. Let me explain quickly why that's so important. Imagine I had a transaction that had 3 inputs going in. So there's a UTXO worth 3 Bitcoins going in, and then one UTXO on the output was equal to 7, and the other UTXO on the output was equal to -4. Right? So we have 3 going in, 7 and -4 going out. Well, 3 is equal to 7 plus -4. Yes, so star is satisfied. However, now we have a UTXO that's worth 7 Bitcoins, which anyone can then spend as if they had 7 Bitcoins. Yeah, so money was all of a sudden created out of thin air, and of course they're going to ignore the -4 output. They're just going to use the 7 Bitcoin output, and sort of all of a sudden money was created out of thin air. So in fact, proving that all the outputs are positive is kind of crucial to prevent money from being created. And so we have to do that as well. The odd thing is that proving that star holds is quite easy. Proving that an equality like this is actually quite easy. This just follows from the rules of exponentiation. Yeah, if I have, well, let me kind of convince you that that's true. If I have a commitment, you can see g to the 533 and g to the 1478. If I multiply these two together, I get g to the 533 plus 1478. Yeah, and I can compare that to the sum, to the product of these two outputs. Yeah, so in fact, checking that a sum holds is actually quite easy. Checking that a value is positive, that turns out to be kind of tricky. Why did I write 2 to the 52 minus 1 here? Well, it turns out that's the denomination of Bitcoin. Yeah, so a Bitcoin can go up to basically Bitcoin has 52 bits of precision for particular amounts, so the amounts can be specified is a 52-bit string, and we have to argue that that 52-bit string is a positive value. Okay, that's the hard part. All right, so what do we do? So our work basically, which we call Bulletproofs, is a very efficient zero-knowledge proof system for proving that a commitment to a value v is positive. Yeah, the value that was committed to, in fact, is positive. And it builds on some earlier work, again, beautiful, beautiful work of Boutel, Sorelli, Chaidos, Groth, and Petit from 2016. We basically kind of improved it somewhat and experimented with it for this particular application. And so what we can do is essentially, if you have an n-bit proof, and so you have a commitment to an n-bit number, and you want to prove that that number is positive, this is what's called a range proof. It turns out, again, I have to write a little bit of math here. It turns out our proof size effectively is logarithmic in the number of bits. Okay, so even if your number is 1,000 bits, the proof will only contain 10 elements in it. Yeah, so it's a very short proof, whereas previously the proofs were much longer. They basically were linear in the size of the value. Yeah, so we kind of went from linear size proofs to logarithmic size proofs. Logarithms, of course, grow much slower. But even more importantly, if you have to do d-proofs, like if you have to prove multiple ranges in a given block, remember every block has like 1,000 transactions in it, and so you have to do like 1,000 of these range proofs in every block. Before, the size of these proofs would just add up. So if you have to do 1,000 proofs, the proof would be 1,000 times bigger than a single proof. In our case, using Bulletproofs, no, you just basically, if you have to do 1,000 proofs, all you do is you add like 10 additional elements, and that's it. And then nothing else changes. And of course, there is no trusted setup, which I won't talk about here. Okay, so these bulletproofs are kind of extremely well suited for confidential transactions. And then just to give you an example, essentially, if you wanted to implement confidential transactions using the previous best zero knowledge system, if you had one transaction, the data that would have to go on the blockchain would be around 4 kilobytes, whereas with bulletproofs, it's only 600 bytes. So even for a single transaction, we save a lot of space on the blockchain. If you wanted to do proofs for like 2 transactions, before everything would scale linearly. For us, things scale much, much better. So instead of 7,000 bytes, we only need 700 bytes. If you want to do 10 proofs, here before you would need 40,000 bytes. We only need 900 bytes. Okay, so again, the amount of data that goes on the blockchain, all these proofs have to go on the blockchain to convince the public. The amount of data using bulletproofs is much, much, much shorter than what was possible before in the case of no trusted setup. And as a result, this makes confidential transactions much, much more practical and easier to deploy in the real world without blowing up the size of the blockchain. Good. So yeah, as I said, this is the bulletproofs are like a very good match for confidential transactions. Just to be concrete, if you wanted to implement confidential transactions without bulletproofs, the blockchain would be like 160 gigabytes. With us, it kind of drops to like 17 gigabytes, so significant savings. And I want you to remember the blockchain is replicated all over the world, right? So everyone would have had to store 160 gigabytes. Here we are providing quite a bit of savings in the amount of storage. The other thing that bulletproofs are good for is proving what's called solving the solvency problem. Yeah, and I'll explain. This is a paper that we wrote in 2015 on how to prove that an exchange is solvent, and I'll talk about that more in just a minute. But I can tell you that in our first results, the proof of solvency, that the exchange actually can support all of its obligations, that proof was 18 gigabytes. Every day would have had to be produced. With bulletproofs, the proof goes down dramatically to something like 60 megabytes, which is much, much, much easier to do in practice. And it turns out bulletproofs can also be used for providing other anonymity mechanisms, which I won't talk about here. Okay, so let's talk about the solvency problem. So that's kind of a really fascinating area in its own right. So let me explain what the solvency problem is. So I hope many of you have heard of Mt. Gox. Yeah, so Mt. Gox is a Bitcoin exchange that essentially held a lot of people's funds. Yeah, so instead of holding the funds yourself, you would give the funds to Mt. Gox, and they presumably would store them for you. Well, unfortunately, through a sequence of mishaps, they basically lost all the funds that were given to them. And just so that you understand, something like $450 million were lost as a result of the Mt. Gox compromise. This was a big deal in the Bitcoin world. It caused a crash in the prices of Bitcoin. This was kind of a very traumatic event for cryptocurrencies and for Bitcoin in particular. But it turns out Mt. Gox was nothing special in that many other exchanges have failed too. Basically, people gave them their funds to hold, and then the exchanges basically lost those funds, and a lot of people lost their cryptocurrency savings. And again, this is why you want to use custodial services, because this is their business. They will not lose, or presumably they're built to not lose your keys. So don't hold the keys yourself. Give them to a custodial service. That's probably the safest thing to do. Okay, so the question is, what can we do about these solvency problems? The fact that so many exchanges have lost the funds given to them. So the question is what to do. And so again, we can use the fact that we're dealing with digital goods to provide what's called a proof of solvency. So what is a proof of solvency? Well, let's see. So every exchange has a bunch of obligations to its customers. This is how much money they owe their customers. And then they have a bunch of assets that they hold, right? So these are basically cryptocurrencies, crypto funds that the exchange owns. And the goal is to prove that the amount of assets is at least as big as the amount of obligations. In fact, if you wanted to support reserve currencies where maybe the assets are only 1/10 of the obligations, you can do that too. But let's stick to the simple case where just assets are bigger than obligations. Okay, this is what solvency means. In the physical world, the way a bank proves that it's solvent is it brings in auditors once a year, and these auditors certify that the bank is solvent. That is not a transparent process. Not transparent, right? Nobody in the public knows what these auditors do. They just certify, but there's no transparency to that process. And the beauty of a cryptocurrency is you can actually transparently prove to the entire world that you're solvent because everything is stored as crypto. What we would like to do, though, is prove that the exchange is solvent without revealing secret internal information that's private to the exchange. Well, this again takes us to the world of zero-knowledge proofs, where you'd like to prove in zero knowledge that you're solvent without revealing anything about your internal business. Okay, so again, that was a beautiful problem for us that we worked on, and as I said, we developed an efficient zero-knowledge protocol for this problem. Yeah, it's kind of remarkable that literally the exchange can run this protocol every day. Yeah, every day it would produce, you don't have to do this once a year like in the physical world. Every morning it would produce a zero-knowledge proof that says, yes, my assets are bigger than my obligations. Nothing would be revealed about its obligations and nothing would be revealed about its assets, and yet the public now is confident that they are solvent. Yeah, so that's what you can do with these proofs of solvency, zero-knowledge proofs of solvency. And as I said, Bulletproof makes this very efficient. It's quite interesting, actually, that if Mt. Gox had run these proofs like on a daily basis, their trouble would have been detected many, many months before they actually had to declare that they're bankrupt. Yeah, in fact, they would have discovered themselves that they cannot run the proof of solvency, and they would have realized that there's a problem much earlier on than when the problem was actually made public. Yeah, so I have to say that bulletproofs have been adopted by a number of projects, and they're actually put in use. Somehow proofs of solvency have not yet been adopted by the industry. So if you know, and if you run an exchange, or if you know an exchange that's interested in deploying a proof of solvency, please get in touch with us. You know, I think this is a useful thing to deploy. I think once exchange does it, all the other exchanges would have to kind of deploy it as well. And you know, it would give us more faith in how these exchanges run. And so generally, this is kind of a nice thing to do. And we, as I said, we can do it, so we might as well. So again, if you're interested in actually deploying and using this, please get in touch with us. All the research that we do is available in the public domain to support the ecosystem. And in fact, we'd be happy to help you deploy this. Okay, so that's kind of what I wanted to say about proofs of solvency. And I have to say, I literally only touched the tip of the iceberg when it comes to cryptocurrencies. It's a huge and fascinating area. All I told you about is just one project that we did this year. We have many, many, many other projects that we do at the CBR, and you know, lots and lots of forward-looking research that we do. If you want to learn more about the work that we do, as I said, go to cbr.stanford.edu and check out our research page. And then in addition, we're also running a class on cryptocurrencies and blockchain technologies. This will be the third time we run this class. We've been doing it for 3 years now. The class is called CF251. It's actually a televised class. So anyone can sign up to this class via sepd.stanford.edu. So anywhere in the world, you're welcome, very welcome to take the class. Either, you know, if you're local, you know, come to our lectures and listen in. If you're remote, you watch it on the web. The class is going to go through a lot of the issues that surround cryptocurrencies, how the crypto works, how the consensus protocols work, how to write smart contracts, what are the upcoming technologies in cryptocurrencies and blockchains. It's a lot of fun to teach this class. Obviously, the students are quite interested in this, and as I said, we'll cover a lot more than I was able to cover here today, so I look forward to seeing you there. Now, I think we're actually running this took a little bit longer than I expected. I hope it was all clear. I was hoping to tell you about another project, which maybe I'll just summarize in 30 seconds and then stop, which is a way to privately aggregate statistics. And again, I put up a link to this project if you want to learn more about what it does, but maybe I can just walk through in 30 seconds and explain what this project does. It's kind of an interesting topic in its own right. So I just want you to be aware that this technology exists, and if it's applicable to you, you know, please use it or get in touch with us, and we'll be happy to help you deploy it. So the problem is basically how does a company learn about its users, aggregate statistics about its user in a privacy-preserving manner? Okay, so today, suppose, let's take a simple application. Suppose you're Twitter, and you want to measure, or sorry, suppose you're an application that measures, I don't know, people's blood pressure. And you want to measure, you know, how does blood pressure correlate to how many minutes a day you use Twitter? Yeah, so every point here corresponds to one user, right? So this user uses Twitter this much, and its blood pressure is this much, right? So if you wanted to kind of build a model for how Twitter usage correlates to blood pressure, this is just a comical application. Nobody actually does this, but if you wanted to build sort of a model for what the correlation is, the way you do that today is basically every user sends the data to the application developer, and then the application developer runs regression to figure out what the model is. Yeah, that's kind of how we do things today. This is highly non-private in the sense that you have to send all your data to the application developer, even though all the application developer cares about is aggregate statistics. Okay, so this is very non-private, and the question is, can we do better? And it turns out we can do better. Basically, what you can do is you can split your data and share and send a share of the data to the stress tracker, which actually reveals nothing to the application developer. You can send another share of the data to, say, Google, which again, on their own, they learn nothing about your data. So this is called secret sharing, where by themselves, they absolutely learn nothing about the individual data, and yet they can actually, together, they can figure out what the model is. Yeah, so this is great. Yeah, this is great. Allows the developer to learn what the model is without learning anything about private data. However, there's a problem. The problem is that someone can come in and send you bogus data. You can see they send a point that's way, 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 way up here, and that causes the whole model to skew. That one point is so off the charts that it causes the whole model to skew. And so what our system can makes it possible to do is basically learn the results, do it with privacy, but also make sure that all the submissions actually lie within a legitimate bound, a valid bound. So you cannot have one submission that will skew up all the results. All right, so that's what the PRIO system does. If you have a need for private aggregation, I guess I'm not going to say much more about this. If you have a need for private aggregation, I would encourage you to go check out this project. This is something that we did again earlier this year. Everything is available online, including code and paper that explains how the system works. And if you'd like to use it, as I said, please get in touch with us, and we'd be happy to help you do that. All right, so I'm going to stop here, and I will open it up for questions. So Joe, take it away.
Great. Well, thank you so much, Dan, for joining us and giving us such a wonderful presentation. Now we'll shoot some questions over to Dan for the end of this presentation. So one of the first questions that came up, and I think it definitely stands out, is why are machines being used to generate Bitcoin hash so highly power hungry?
Yes, that's a great question. Right. So you're asking about the proof of work. So I guess this is related to the consensus part, which we didn't quite talk about here. So let's see. So Bitcoin uses this proof of work mechanism so that the more power you invest as a miner, the more likely you are to be minting the next block. And I should say that whoever mints the block gets what's called a block reward, the Coinbase, which is essentially an amount of Bitcoin that then you as a miner own. So the reason for this proof of work mechanism is actually very simple to understand, in that effectively it's a way to randomly choose a miner from the set of all miners in the system. Yeah. So everybody invests a certain amount of energy in trying to solve a particular puzzle. Whoever solves the puzzle is kind of wins the lottery and gets to mint the next block, which then pays back to that miner. Okay, so effectively a proof of work is what we have come to call a randomness beacon. Yeah, if you have, like, say, 1,000 miners, then the proof of work is basically a way to choose at random from this set of 1,000 miners in a way that no one can bias, right? So everybody tries to solve the challenge that was embedded in the block, and whoever solves it is the one that actually gets the block reward. So basically, proof of work is a way is one way to implement a randomness beacon, that chooses a miner at random. But now there have been many proposals for other randomness beacons that actually are not that power hungry, that don't require burning so much energy. So in fact, this is kind of, as I said, generation 1 blockchains require proof of work. The 3rd generation blockchains are actually starting to move away from proof of work. And just to give you some examples, there's a lot of, there are many experiments with proof of stake. So rather than generating randomness by solving a hard challenge, we can generate randomness by basically requiring everybody to prove some stake. And if they misbehave, they lose that stake. So there are several experiments with that. There's beautiful work on using proof of space instead of proof of work. So a project called Chia is doing that. Proof of space means that rather than proving that you own a lot of CPUs, you prove that you own a lot of disks. And disks, so you have a lot of storage. And disks themselves actually don't consume that much power, so it's going to be much more eco-friendly. It's going to be a much more eco-friendly way to generate randomness, to sort of choose a miner at random. In fact, Chia calls it farming instead of mining because it's so much more eco-friendly. And so we're actually going to be moving away eventually from proof of work, and this mining process is not going to take that much energy. But again, to answer your question, yeah, in one sentence, essentially, it's the proof of work is a way to choose a random miner that will then mint the next block.
Great, thank you for that. Another question, and this came up a few times. If the blockchain info can't be deleted, how was Mt. Gox crypto disappear? Like, how did it get stolen?
Yes. Well, well, the information is still on the blockchain. We can still see that it was stolen. So it's not that the data was deleted from the blockchain. What happened was essentially there were a couple of things that happened. Essentially, Mt. Gox. So people sent their money to their cryptocurrencies to Mt. Gox. Mt. Gox consolidated it into their own assets, and then unfortunately, due to bugs in the system, an attacker was able to withdraw more money than the attacker deposited. So even though all the money was pooled together, Mt. Gox paid out more than it was supposed to the particular attackers, and as a result, it's all recorded on the blockchain. They basically lost the funds that were given to them. Essentially, the funds were transferred to another malicious user, and so so the data was not removed from the blockchain. It's just that the funds moved where they were not supposed to move.
And in follow-up to that, if the ledger is always there and you could see the transaction, how are they not able to identify who the attacker was?
Well, that's a good question too, right? So if the attacker moves the funds to different addresses, you can definitely follow the money and see where the addresses are. But the attacker might actually just leave the funds on the blockchain and never actually translate them to a physical entity. So right, that could still. Then, if there's no interaction with the physical world, you're not going to figure out what the physical entity is associated with a particular address, right? So, the funds are just sitting there. Maybe in a couple of decades, someone will withdraw them, but right now they're just there, and we have no idea who they belong to.
Great.
Yeah.
And this last question. This last question might be a very timely question. So by definition, there is no privacy. How does this play into privacy laws?
Oh my God. Okay, so let's just be precise here. It's not quite. You're saying there's no privacy in the blockchain. Mm-hmm. That's not quite true. That's not quite true. So in the Bitcoin system, as is, yes, when you put data on the blockchain, the whole world can see it. When you make transactions, the whole world can see the transactions. The work that I described here basically allows you to protect the amounts. Yeah, so still you will know who paid who, but the amounts will be hidden. There are other blockchains like Zcash, like Monero, that actually protect everything. Yeah, they're completely private. So in Zcash, for example, you have no idea who's paying who, what the amounts are. Just nothing is hidden. All you can do is you can verify that transactions are valid, but you have no idea what's in the transaction. So Zcash actually is a very, very good fit for business needs. If you wanted to transact with your supplier and not even reveal who your supplier is, Zcash is a good way to do it. So to say that there's no privacy is just not true. Yeah, there are blockchains that do provide a very strong notion of privacy. It's just that the most widely used ones, Bitcoin, Ethereum, and so on, at the fundamental layer, they don't provide privacy. But again, you can build things on top of them that will provide privacy as well. So yeah, so just let's make sure we're precise and accurate there.
Great. Well, thank you so much for your time today, Dan. We hope you all enjoyed this presentation about crypto and blockchains. And if you have further questions, please reach out to our client services team. Have a great rest of your day.
Yeah, thanks everyone. This was a lot of fun, and feel free to send us more questions.